All right, the stream has lifted off on the YouTube side of things as well.
Fantastic. Well then, hello and welcome back to another edition of Astronomy at Home, the last one of the year, brought to you by the DiRAC Institute and Astronomy on Tap Seattle. We're so glad you could join us again for a night of incredible science. We have a very special and incredible talk coming up for you, but before we start, some of the usual reminders. We'll have our Q&A session with the speaker immediately following the talk. So feel free to add questions along the way, either in the Zoom chat or the YouTube chat if you're following along there. We will not be having our usual Instagram Live interview tonight after the talk, so make sure to get your questions in during the Q&A. All right, let's get started. As I mentioned, we have an extra special guest for you tonight. He served as a NASA astronaut for 12 years, during which he flew aboard the Space Shuttle twice and did a 6-month tour on the International Space Station. Now he is the executive director of the Asteroid Institute, a program of the B612 Foundation. Please give a very warm welcome to Dr. Ed Lu.
Thank you, everyone, and I hope everyone has a appropriate beverage, whatever that may be. So I would like to thank everyone in Seattle and in particular at the DiRAC Institute and University of Washington for hosting this series. And I'd like to talk tonight about, the talk is titled Charting the High Frontier of Space, and you'll see why I say the high frontier, but it's about mapping the solar system and why I believe that's so important. So what do I mean? So let's get started. Let's roll the clock back to a photograph I took sometime in mid-2003. This is a photograph of the northeast part of the United States. And if you look carefully, left is sort of up and to the left here. You can see you'll see that we're actually somewhere above Michigan, perhaps Wisconsin actually. You can see Lake Ontario and Lake Erie off in the distance, but circled in the white circle there is an interesting spot on Earth. I used to love looking at this place as we went overhead because it's the location of a very large asteroid impact, which took place about 100 million years ago. It's located in an area called Sudbury, Ontario in Canada. And it is actually sort of a neat combination of economics, finance, astronomy, all thrown together, because this large asteroid, which happened to be an iron nickel asteroid, struck the Earth there. It was large enough to have caused a mass extinction, and it may have at that time, although the fossil record's a little sketchy at that point. But it also left behind some of the world's richest deposits of iron and nickel. And in fact, the INCO Corporation, which stands for International Nickel and Copper Corporation, set up its mines there around the turn of the last century, and in fact was one of the largest mining corporations in the world. And when they originally set up the Dow Industrial Corporations, it was one of the original Dow 30 corporations. So here's sort of an instance where astronomy has greatly affected the economy of the Earth. And I just think it's a neat little story there. A more recent incident involving an asteroid is this one, Chelyabinsk, 2013, which is a city in Russia. And due to the fact that there's a lot of insurance fraud in Russia, there are a lot of dash cams. And people caught tons of videos of this 19-meter asteroid. So it's about the size of like a restaurant, maybe. Something like that, streaking across the sky at Mach 50 or so, and exploding in the atmosphere just after passing the city of Chelyabinsk, perhaps 100 kilometers away from the city. Now, even at that great distance, its explosion was large enough, about 30 times the size of the bomb dropped over Hiroshima, that the shock wave, when it propagated to the city, blew out essentially every window in the city, sent about 2,500 people to the hospital, collapsed a few buildings. Those who were closer to near where it exploded actually got 2nd and 3rd degree burns on their skin just by looking at it. Perhaps that also tells you a little something about how much sunlight Russians get in the middle of winter. But this tiny little asteroid, which exploded after hitting the atmosphere, had no notice. And the reason it had no notice is actually not surprising to those in the know, because greater than 99% of the asteroids in our solar system that are large enough to cause damage should they hit the Earth are currently uncharted. We have no idea where they are. So the fact that an asteroid like of this size arrives unannounced is actually what would happen the vast majority of the time. We don't know where they are. So now I'm going to switch gears a little bit and talk about the opening of new frontiers. And I'll give you a little shorthand for understanding the thesis that I've got, which is fear, greed, and curiosity. So remember that. So my thesis is that the opening of new frontiers is enabled by mapping in almost all cases. And I'm going to give you some examples of famous maps that helped open up frontiers. So early 1500s, this is just about a decade after Columbus, this map came up, and it was called the Cantino Planisphere. And already you can see within 10 years after Columbus, there's a pretty decent of idea of where the locations of things are. Of course, most of the continent of North America is missing, but you can see India, Africa is pretty well done there, but the coast of South America is in there, and what's now called the some islands in the Caribbean are there. And it was a very influential map because it was the first map to really begin to look at compass directions as opposed to just navigating along the edges of things. It's about crossing the ocean. If you can see the paths written out across the ocean there. At the time, all the major powers knew that there were riches to be obtained if you could chart a course to Asia for trading purposes. They knew that there were military advantages if you had a better map than anybody else. And of course, they were interested in just what's out there. And because of that, they competed to generate the best maps. In fact, this map, which was funded by, it's a little unclear. It was funded by nobility and partially also, it appears the Portuguese government, was stolen multiple times. It was valuable enough that it exchanged hands many times. Some by payment, some by not, stolen. Disappeared for a number of centuries and wasn't recovered until it was found on the wall of a butcher shop in Modena, Italy, about 30 years ago. So very interesting. But this gives you an indication of the importance that the great powers of the day put upon mapping. They knew mapping was strategic. Here's another interesting thing. It's a map from Lewis and Clark. If you remember when the United States first purchased the Louisiana Purchase, the very first thing that President Thomas Jefferson did was he sent Lewis and Clark on the Corps of Discovery, they were called, to go map the western part of what became the United States for samples of flora and fauna, for navigable routes and points of defense. Finally, here's another interesting frontier. It's not so much of a physical frontier as sort of a metaphysical one, but the human genome is actually, you could consider it a frontier. And as we gain the capability to understand it about 25 years ago, the very first thing we had to do was to map it. Why? Because we wanted to know the physical relationship of genes. We wanted to be able to cure diseases. And we wanted to be able to understand how human beings came about, because it's written in our genetic code. So all three of these things were motivated by the same three things, which my shorthand notation is fear, greed, and curiosity. Fear, which is defense. In this case, it's defense against diseases, or in the case of the Cantino Planisphere, was defense against the other great European powers. It's greed. It was, in this case, it's for developing medicines. For the case of the other maps, it was for trade routes. And curiosity, for science, for just understanding where things are. And so maps have always been key to the opening of frontiers. So my question is, what's the next great frontier? And I'm going to make a case that one of our next great frontiers is space, and that there's been a fundamental shift just in the last, I'd say, 7 or 8 years in what's happening in space that you should know about. So what I'm plotting here on the right-hand side of this is the number of spacecraft launched each year, color-coded by whether or not, by what country they're from, or whether or not they're private. So this graph stops in 2018. But if you look at 2020, the number is well through the top of this. It's well over 1,000 active satellites were launched in 2020. But what the interesting thing to note is that right now, the green coloration in that map utterly dominates. Private satellites are more than 85%, 90% of all satellites launched today. That's an interesting shift. So not only is the number increasing, but the mix is changed. If you look at the total economy of space, and this is estimated by economists from various investment banks and so on, their best guess is that the world space economy, the revenues of all the companies operating in space and the money spent by governments, is approaching $1 trillion. And it's actually growing at a very interesting rate. It's growing at about, it varies from year to year, but it's between 8 and 12% per year, which puts it at China-like growth rates. And if you extrapolate that, and it's always a danger to extrapolate in the future especially with exponentials, but you can see that the economy of space could actually dominate over many countries within a few decades. Anybody who's ever been to China in the 1990s knows that 10% growth rate above the rest of the world, you give that 20 years and it makes an enormous difference. And that's exactly how space is growing compared to the terrestrial economy. So something interesting is up here. And of course, this is one of my old favorite comics. My argument is that space, in fact, is going to become an everyday part of what we human beings do. If it already is for many sectors, but even more so. And even on an economic front, it's going to dominate. I just like this picture. So my argument is that this space frontier, just like every other frontier before it, will be opened up. The opening of it will be enabled by mapping. So what do I mean by that? Well, where is everything in our solar system? Our solar system is primarily, almost entirely, formed of asteroids in terms of numbers of objects. This is an actual plot of where the objects are. This is the Earth, where my cursor is. There's the Sun, Mercury, Venus. This is the asteroid belt. By mass, of course, the solar system is dominated by the Sun and Jupiter, but by object number, by locations, it's dominated by asteroids. And remember when I said that 99% of the asteroids are uncharted? Well, it turns out you have to say larger than a certain amount, but let's say 99% of those large enough so if they hit the Earth, they would cause great damage or would be of interest as a place to visit, sort of essentially the same thing, are uncharted. So in some sense, we're a bit like the 1500s or maybe the 1400s, where the map of the world is basically empty. Or so the map of the solar system is, we've got the big continents, we know where those are, that would be the planets. But all of the islands, all the archipelagos, all of the rest of the stuff, big question mark in the middle of the map. Where are they? The vast majority of them uncharted. So why would we want to map space? Why would we want to know the locations of everything? And keep in mind that the term location here is a little bit different than you might think of it in a static map, because remember I showed you everything is moving. So it's an interesting map in that everything is moving. But the same three reasons I just mentioned are, I think, why we want to do this. Number one, science. Well, the geology, the composition, the structure of asteroids tells us about how the solar system formed, how our planet formed, and how we ended up where we are. This is an interesting photograph. It's a mission to an asteroid. This is the shadow of the spacecraft dropping in to pick up a sample. This sample actually was returned to Earth this last weekend. It landed on a capsule in Australia. It was picked up by the Japanese space. It's a Japanese space agency mission called Hayabusa 2. So I would argue that an important reason for wanting to map all these things is so that we can understand the formation and evolution of our own solar system. Science, curiosity. What about greed? What about commerce? Remember, I just showed you that the economy of space is growing at a sort of rather unbelievable rate. And if that continues, then this is going to be an interesting thing, because like everything else, an important part of commerce is knowing where things are. This was, the importance of space from an economic standpoint was sort of first pointed out by Jerry O'Neill when he wrote this seminal book back in the 60s called The High Frontier. And he talked about eventual settlements of human beings throughout the solar system. And I believe it may actually happen. When I said, where things are is super important, this is an interesting map. It's just a map of the Permian Basin in Texas showing the locations of natural gas fields and how all the various companies there have laid claims to various locations of mineral rights, essentially. And one of the very first things happens when things open up is this ability to lay claims, and that requires maps. So my contention is, just like everything else, if there is commerce in some location, you need maps. You need maps to show where things are and how you get there. Navigable routes, in the case of, back in, Lewis and Clark, navigable routes meant, rivers and passes. Nowadays, it's trajectories. Well, what about fear? What about defense? And the reason this is important, because as I pointed out, sometimes these asteroids hit the Earth. And if you know where the asteroids are, if you know where they're going, then I can tell you which ones might hit the Earth and when. And if you know that, then you can actually protect the Earth from being hit by asteroids. So this is a process that's gone on for billions of years on Earth. The last sort of major one prior to the one in 2013 was Tunguska in 1908. Took out an area roughly the size of London. This is the location of that. You can, even to this day, the trees are all laid flat out for hundreds of square miles, and the area of destruction is larger than any large city. So, and this was a small asteroid, just 45 meters across. And if you don't know where these asteroids are, then sort of by definition, you can't stop one from hitting. But if you know where they are, it's actually almost a trivial thing to prevent an asteroid from hitting the Earth, because if you know, and here I'm talking about at least a decade in advance, which is what you expect from our mapping of the solar system, then a change in the velocity of an asteroid by just a few millimeters per second is enough in general to keep that asteroid from hitting the Earth. And that's as simple as running into it with a small spacecraft. So super simple. You don't, all the garbage you see in the movies, believe it or not realistic. In fact, NASA is actually going to do a test of this next year, launching a mission in October called DART, Double Asteroid Redirect Test, in which they're actually going to deflect by a tiny, tiny, tiny amount an asteroid and measure the change in its trajectory. So that's fairly straightforward. The hard part being, we need a map of where all these asteroids are, okay? So how do we build it? This turns out to be one of the things that's going on right up in Seattle at the University of Washington. The LSST project, which is in the middle here, will be far and away the largest discoverer of asteroids of any machine ever built by human beings. Currently, the number one is the one on the upper left. That is the Pan-STARRS Observatory in Hawaii. There are a number of other observatories that have tracked. Right now, we have tracked, of the near-Earth asteroids, those that could hit the Earth, about 20,000 of those are tracked at some level, not all very well, but at some level. This machine in the middle, which will open up in just a few years, we expect to find roughly a factor of 10 times more than that. So we'll go from knowing where sort of 1% of the asteroids are to 10%. It's a big improvement. Still not quite there, but it is an enormous improvement. To do better than that, you're going to have to figure out ways of going to space. So this is sort of just a generic spacecraft. We can talk about that later in questions if people have them. But essentially what you do is with these asteroids is you observe them with telescopes, and you observe them multiple times. And you look at the location of where you see it on the sky. And then you use math. You use our knowledge of how gravity operates. And I say, what orbits are consistent with all the observations of that particular asteroid? And how certain am I of that? And that process called orbit determination is how you actually build the map. Then what you actually have for each asteroid is a location as a function of time. It's a trajectory. It's not just a single position. So if you think about what a map actually is, it's actually four-dimensional. Unlike a flat map, it has three spatial dimensions, but also a time dimension. All of these asteroids in this map are moving. And so what's actually important in most cases isn't where the asteroid is right now, but where it's going to be. Will it hit the Earth? If I'm sending a mission there, if I'm trying to get there, I'm going to aim for where it's going to be, not where it is right now. And I too have to follow the laws of orbital mechanics, laws of gravitation. And so this is a sort of an interesting map in that it's four-dimensional. And this is, in fact, is what we are building in collaboration with researchers at UW. I thought I'd show something interesting here, which is a quick little video of, well, in fact, let me just do this as a live demo. Let me just show you an example of what we can do by taking a look at an actual asteroid and where it's going to be. Let me show you a particular asteroid. Here we go. This is an asteroid which came past the Earth very close on Election Day. People dubbed it the Election Day asteroid. It was small, just a few, about the size of a car, about 6 feet across. So even if it hit the Earth, it was no big deal. But just like there's an uncertainty in where the location of a storm is going. So for instance, you may have seen hurricane tracking cones where they show where they can spread out to as time goes by. So in other words, I don't know for certain that a storm is going to hit Miami, but I might know that it's going to be somewhere in Florida, and they show you a graphical map showing where those things might go. Well, you can do similar things for asteroids, and we did one for this one, showed that if this particular asteroid was going to hit the Earth, it was going to hit the Earth only on this little line here. And if it was going to come near the Earth, these are the areas near the Earth that it could come near. So it had, in other words, it may not have come close to the Earth, but that if it did hit the Earth, it would be on a particular line. So that's the kind of thing that you can do when you have an asteroid map of the solar system. So I'll stop blabbering right now, and I'll open it up for questions. But I do want to quickly thank our donors. Our B612 Foundation is a nonprofit. We are supported by the generosity of our donors. And so these are the folks who have made all this work happen over the last decade or so. And so I do always want to thank our donors for that. So I'll leave it there and see if folks have questions.
Great. Thank you so much. I'm going to clap for everybody in the audience who I'm sure is clapping along.
I'm going to take a swig of beer.
Oh, yes, absolutely. Got to freshen up. And I believe we have one question on YouTube, if you want to take it away, Jim. Oh.
Jim is muted.
And if anyone's following along in the Zoom, feel free to put your questions in the chat as well. Well, I have a question that I was interested in as you did that kind of live demo for us. And so is that, I guess, how far back in the future can we, start looking, right? Like there's kind of, there are so many asteroids out there. And so like how long ago, maybe specifically for this example, the Election Day asteroid, like how long in advance are you expecting to be able to track these?
Well, many decades. So, in fact, for sort of a well-tracked asteroid, and not all of them are well-tracked, but those which are well-tracked, we can calculate their future position out to about 100 years.
So we've got a pretty good defense coming up this way.
Well, that's the idea. But remember, not all asteroids are well tracked. And this is just simply a function of how often and for how long you have observed an asteroid. This is sort of similar to if somebody's throwing a ball at you and I give you a snapshot of them throwing the ball, but I give you one snapshot of their arm. I can't really tell where that asteroid, where that ball's going. But if I gave you a series of 2 or 3 pictures of them throwing it, I get a little idea of where that ball's moving. But if you gave me a whole series of pictures as this thing is flying through the air on its way towards me, then I have a pretty good idea of where it's going to be. And it's calculating trajectories is no different than that.
I see. All right. Well, we have a related question that I see in the chat. Does the loss of planetary radar compatibility at Arecibo reduce the capability to rule out collision risk for newly discovered objects, or can other facilities provide that?
That's a great question. For those who don't know, the planetary radar at Arecibo actually collapsed last week. And so it is no more. And one of the things about radar facilities that's different than the telescopes is that you can tell not just the position on the sky, but the distance. And that means that you can actually calculate the trajectory that much better when you have radar observations. They complement the telescopic observations very well. Now, the vast majority of asteroids never come close enough to the Earth that you could ever hope to get radar on them, but some do. And it turns out that the ones that have a chance of hitting the Earth often come close to the Earth. And that's why that radar was particularly important for the subject of planetary defense, preventing them from hitting the Earth. Now, there are other radars, particularly one in Goldstone, that have such capability, but they're not as powerful. This Arecibo was far and away the most powerful one. In other words, it could see asteroids at greater distance from the Earth, and that was very important because, again, most times these asteroids don't come close enough to the Earth to be picked up by the radar. So this is definitely a loss. It sort of remains to be seen whether or not we will eventually get some sort of replacement capability for that or not. It was a very expensive instrument, and it was built sort of almost 50 years ago.
Ed, we've got a few good questions over here on the YouTube side of things too. Let me shoot a couple your way here. The first one is from Hendrik, who wonders if you could say a few words about what it was like being on the space station the first time you could see Earth, and what that view was like.
Sure. The very first time I saw the Earth from space was actually from the Space Shuttle, a number of years before I ever visited the space station. And I had seen thousands of pictures of the Earth before from space, but there's no substitute for floating in a window of a spaceship, looking out the window and seeing that. And it was just amazing. It almost took your breath away. But the problem is, immediately after launch, you're actually quite busy. You've got a lot of things you have to do. We have a maneuver shortly thereafter, so you can't get too distracted right away. You actually have things to do.
Right, can I improvise another question? Would you go back to space?
Sure, I'd love to go back. Can you buy me a ticket?
No. That's a good question, though. Another question here, sort of on that line of questioning here, is this seems like a pretty big challenge, hunting for asteroids, not going to space. How do we raise public funding? How do we raise public interest? I know the Institute is doing a lot of work, but how do we get the people involved?
Well, I think our next great challenge is simply dealing with the data that's going to come from the LSST telescope. Now that is about to turn on. So like I said, it's going to increase the number of asteroids that we've seen by a factor of 10. So we've got an enormous challenge just dealing with what's going to come off of that telescope alone. We are thinking about things beyond that, like I said, and they may or may not be as expensive. As technology marches on, as we move towards greater capabilities of sensors, that may change, and cheaper ability to launch things into space, that may change.
All right, we've got another question from Zoom. So if right now we're unable to track all asteroids, is there a way to select asteroids that are more likely to come into near Earth or in Earth impact and then focus on those?
Well, only in a statistical sense, that there are orbits in which are slightly more likely to hit the Earth, but it's by no means a strong correlation, which means that you really do just need to start mapping everything and find the ones that actually, when you look ahead decades, have a chance of hitting the Earth. So, and I don't want to give the impression this is an impossible thing to do. Remember that the asteroids that we found thus far tend to be the largest of them. So we found the vast majority of the large ones, i.e. the ones that would wipe out human civilization or cause a mass extinction. Those types of things are mostly found. And now we're looking for the ones that might only wipe out, the Earth economy for a few centuries, that kind of thing. Still pretty bad, but not, at least we're not all dead. Eventually we want to get down to the things that would only be the size of a very large nuclear weapon. That's, I think, where we want to get down to. But LSST will take us down to those that are sort of 100 megatons ish, in a few hundred megatons, call it, in impact energy. And that's still a horrendous thing, but if we find most of them, then at least then we would be safeguarded from those. Progress.
Absolutely. And kind of a related question, getting at the origin, like what is the original origin of most of these asteroids? Some suggested by the question was extinct planet, collapsed many parts of dust clouds. Can you speak to that?
Well, there's a lot of sources for these asteroids. Most of these things were formed. They were actually a planet that really never quite made it. The origin of most of them is the asteroid belt, which was a planet that didn't form, actually. And what happens to them there is that sometimes they get too close to Jupiter, or they have what's called a resonance. It's like when you push a swing at just the right velocity or at just the right timing. These things get thrown into different orbits, and that's how some of them end up in other parts of the solar system, like near us, near where the Earth is. In fact, though, as I mentioned before, the exact number of asteroids in different orbits, the distribution of their orbits actually tells us about the evolution of the solar system. It tells us about how Jupiter's orbit has changed, how Mars's orbit has changed, how the size of the solar system is actually, the size of the orbits in the solar system have changed over the years, and that's really an interesting thing that you can back out of the distribution of asteroids.
So there's kind of a related question here on the YouTube side. You've talked a lot about the asteroids that we have that are tracked, that have known trajectories, but you've talked about just a second ago asteroids getting kicked around gravitationally. But what about asteroids that might run into each other and like bounce off each other? Is that an effect that can happen in this asteroid field kind of sense?
Yeah, asteroids can hit each other. In fact, if you look at, when you get a spacecraft next to an asteroid, you'll see craters on it. But that's asteroid hitting asteroid, right? Asteroids in general are pretty tiny, and so they mostly interact gravitationally with the planets nearby. In fact, the major source of things that moves things around is planets, Jupiter in particular. But each of the planets, when something comes very close, will really gravitationally change the orbit of that asteroid, often by a lot.
And one other question. You talked about greed as one of the motivating factors in some of these.
Yeah, greed's just a shorthand notation for commerce. Let's put it that way.
Sure. Do you worry about greed and its role? I mean, if we do discover something very impactful, maybe pun intended, do you worry about how greed and economics are going to play into how that data is shared and how solutions are generated?
No, I actually think it's going to be the other way around. It's going to be the search for commerce and value that's going to lead to the developments which allow us to map the solar system. In the sense that I'm in favor of, things that could help fund these things, but really it's the economy that drives innovation, which drives technology, in some sort of cycle. And that's how we make progress.
I have a related question on the commerce side of things from the Zoom side. Do you have any thoughts on the, gentle tensions between commerce or, making money through launching commercial satellites and the need for clear skies to enable instruments such as LSST?
Yeah, I think sometimes you do need regulations. We've seen this before, right? There's a reason we have environmental regulations here on Earth, because sometimes the motivations aren't aligned properly, and sometimes you need to make it so that there's a cost to doing things that degrade things for everybody else. And that's the purpose of regulations, and I think that's going to come into play here in Earth orbit here fairly soon.
One more technical question that popped up on YouTube, Ed. How does the new telescopes like LSST, how do they see these tiny dark asteroids that are so far out in space? It seems like it'd be very difficult to see something that small, that far away, and that dark.
Well, the secret to LSST is it is a gigantic mirror. The bigger the mirror, the more light you can collect. Okay. And that's true up until you get to the point where the mirrors are just so big that they become sort of impractical. And LSST is about reaching that point. It's hard to make a mirror larger than that, still, made out of materials that we know of. So it might be sort of the rough end of the line of this type of telescope, in terms of, and which might mean going to space with smaller telescopes. That's what I was sort of hinting at, that in the future. Obviously, the LSST is where the action is at least for the next decade or so, though.
When you showed that picture, you tempted us with that picture. Do you want to say something about that small telescope in space?
Yeah, well, it turns out that right now we take there's sort of two things you can do. You can make your telescope larger, or you can take a longer exposure, right? Get more light. Problem is with longer exposures is the objects are moving. And if they're moving and you take a long exposure, well, then you spread the light out across various pixels. And if this thing is very, very dim, not brighter than the background, in fact, the background noise is often brighter than the asteroid itself, you won't see it. It won't get any brighter by taking a longer exposure because it's just smeared out across all the noise. Now, it turns out that you can correct for that by taking your telescope and following along with the asteroid, right? Keeping the asteroid in one spot. Now I can take a really long exposure. Problem is that only works if I knew where the asteroid was to begin with. But remember, the whole idea is I'm trying to discover asteroids that I don't know where they are. So I don't know which way they're going or where they're located. So I can't do that. But we have pioneered a technique, along with others, of trying a different tack, which is if you have fast enough graphics processing, you could just say, let's just assume there's an asteroid every location, moving in any possible velocity. And let's try every one of these in software, without moving the telescope, but in software, taking a series of images and adding them up. It turns into a tremendously hard computing problem, not difficult, but requiring an awful lot of computational effort, speed, that up until recently hasn't been available. But fast graphics processes, thanks to, I guess, greed, if you'd like, to the video game industry, have become very, very commonplace and inexpensive. And so if you can get those to work in space, you can actually use small telescopes and long exposures, very, very long exposures, to correct for this motion and hunt for these asteroids. And so we think that's going to be possible in a few years.
That's great. And speaking to something you kind of mentioned in your answer, what do we do about long period comets or perhaps asteroids that can come in from behind the sun? Are there any thoughts about finding these with ground-based facilities?
Yeah, long period comets is a different problem. Remember, I showed you that map, where all the asteroids are. If you expand the scale out by a factor of 100, make that, step back by a factor of 100, so that that entire thing is in the middle, then that's where the comets are coming from. Really, really, really far out. They'll sit out there for, decades, and then they come screaming into the solar system, shoot past the sun, and they go back out there for another century. Okay, that's the type of orbits that they tend to be on. And so they become very, very difficult to spot, because they're 100 times further away, which makes them really, really dim. And so as of right now, this is a much more difficult problem. But the point of it is, though, that there are roughly 100 times more large asteroids than there are large comets. And so, the fact that I can't solve the comet problem, I don't think is a reason not to solve the asteroid problem. In the same way that just because I can't cure cancer doesn't mean I shouldn't try and solve heart disease.
Well, maybe on the, complete other side of that, we have a question from the Zoom. Is it a fantasy to capture an asteroid for the minerals it might contain, and is bringing the asteroid closer to Earth too sketchy to feasibly consider?
As of right now, we don't really have the technology to do this for anything large. Right now, people are talking about the beginnings of how you would begin to manipulate asteroids, and I think someday that's going to happen. I also think that someday the goal isn't going to be to bring them back to Earth, but to use them in where they are. Because at some point, if the economy of space becomes larger than that of the Earth, and that is actually conceivable, then where they need to be taken, where those raw materials need to be taken, is somewhere else in space. If you think about today, here in what's now the United States, we're not making things here, or growing things here to ship them all back to England. Right? They're being used here. The majority of stuff that comes from the United States is used here in the United States. It's now larger than England. And I think the same thing is going to be true someday in space. And remember the power of that exponential increase. At the current growth rates, we aren't talking thousands of years until the space economy is larger than the terrestrial economy. You're talking a century. That's actually quite interesting. Again, growth rates may change. That could change, up and down. There's going to be, just like every other, economic sphere, there's crashes, there's ups and downs and that sort of stuff. But if these trends continue, then that's what you're looking at. I think Jeff Bezos said in the future, he goes, Earth is going to be light industrial zoned.
All right. We are, I think, on our last question of the night. So the smaller telescope deployment idea is being called tantalizingly interesting, but asking kind of more details about that. Can you deploy an array of smaller mirrors, and would that be A, more cost effective, and B, provide a larger sum surface area for collection?
Yeah, it's not actually having small mirrors be working together in a larger size, which is actually something that they do in many telescopes, like the Keck Observatory is one made of smaller mirrors. What we're actually talking about is doing this in space with small telescopes, independent small telescopes. And in the end, actually, I do believe it's going to be far, far cheaper. We're not there yet, but I think that day's coming.
Well, I feel like that is a very exciting note to end on. Thank you again, Dr. Liu, for joining us here at Astronomy at Home. And thank you, everyone who's joined us on Zoom, who's joined us on the YouTube channel. We thank you for spending the first night of Hanukkah with us. Happy Hanukkah to all of you that are celebrating. I hope you have a wonderful rest of your year, your happy holidays for the rest of the month. And thank you again for joining us. Thank you, Dr. Liu. We'll see you next year.
Thank you, everybody, and have a great holidays.